linear maps, or there is alternative name which is called linear transformation or linear transformations, and there's another alternative name which I use very often, linear operators. All three names are identical, and that's what we're going to study for the next few weeks, and actually for the rest of the semester. We're going to split the study in two different sections. First, we're going to discuss the elementary properties of linear maps or linear transformations, and then we're going to study what is called the spectral properties, a little bit of spectral properties of linear maps or linear transformations. So what is it? By definition, if I have two quadruples this time, so each of them individually is a linear space. Remember, linear space is something which comes with as a quadruple, the objects, the plus operation, the times operation, and the field of scalars. So if you have two such quadruples, the only requirement for these two quadruples is that they share the same field of scalars. The rest may be totally different, so this plus and this dot may be different from this plus and this dot. Now, if you have a mapping from one linear space to the other linear space, so that's the typical that's notation which we read a mapping from V to W. This will be called a linear mapping or linear map if and only if two conditions are satisfied. First one is the image of a sum of two vectors is the sum of the images of those vectors, and that is true for every two vectors from your space V. And the second property is that the image of the scaled vector is the scaled of the image of the original vector x, like so. And that is, again, this should be true for any vector x from the vector space and any scalar from your field of scalars. Just a minor comment here. When I write something like this, you have to realize this plus and this plus, it's different pluses. This plus on the left-hand side, that's the plus from this quadruple. That's the plus within the V vector space. This plus, it's the plus within the W vector space, because the image t of x and t of y, these are the vectors from my image vector space. Sometimes this is called the domain. This vector space, which is on the left in this notation, is called the domain of t. Sometimes it's called the domain of t, and this one is called the codomain of t. That's a sort of terminology you will meet very often here, so that's why I'm fixing this. Right from the beginning, we can just establish some few very simple properties of linear transformations, which we're going to use very often, and I'm going to do it here right on the slide. Simple properties. The first one I'd like to observe is this one. If you apply a linear transformation to a zero vector, if you apply a linear transformation to a zero vector, you can always do something like this. You can make the observation that the zero vector can always be factored like a zero scalar times a zero vector. That's something we know from our studies of vector spaces. Then you can use the property B of linear maps or linear transformations. You can take the factor and pull it out like this. And then this dot will be already dot in the codomain in a W vector space. And we know that if you multiply any vector by a zero vector, you will end up with a zero vector. I'm sorry, I meant to say if you multiply any vector by a zero scalar, you will end up with a zero vector. And that's why the result is a zero vector. And that's the first trivial observation about the linear maps. Linear maps always take zero vectors into zero vectors. Again, I emphasize, even though this zero vector and this zero vector looks totally identical, essentially it's a totally different zero vectors. One of them is the zero vector in the domain V, the other one is a zero vector in the codomain. And in general, it may be two totally different vector spaces with totally different nature. One of them may be n tuples, the other ones may be functions, for instance. Second property, again, it's a elementary observation, but it's useful sometimes when you, especially it's useful sometimes when you try to disprove that something is linear transformation. First, you try these two. It goes like this. The linear transformation of the negative of a vector, we can always, again, modify the negative of the vector into the product of the -1 scalar and the original vector x. Then I can use the property b again of my linear transformation, this one, and factor out -1. That will give me something like this. And we know when we multiply a vector by -1, it's basically the negative of that vector. So that is negative of t of x. Again, I emphasize that this negative and this negative, it's two different negatives. This negative, it's in the domain, and this is negative in the codomain. They may be totally different. And that is true for any vector in my original vector space V. And the third property, which I decided to mention on this slide straight away, it's the one which combines these two in a sort of mathematical induction way. So it says like this: if you have your linear transformation or linear map, and you apply this linear transformation to a linear combination of vectors, like this, you can always argue like so. You can use the property A, where in the place of x vector you use this piece, and in the place of y vector you use this piece, this large piece. If you do that, then you have you can split your, or you can convert your expression into something like this. You see, here's my x piece for the B property, for the property A, and here's my y piece for the property A. Now, if I use the property B for the first piece, I can take the lambda scalar out like this. I'm going to keep the second term as it is. And what can I see? I can see that if I apply my t to a linear combination, effectively, I can pull out the first term together with the factor, and my linear combination reduces to by one term. If I do now this trick n times, then I can pull this second term similarly, third term similarly, and all the rest of them. And I can conclude that if I repeat this n times, that's where the mathematical induction actually is in order. I can say that the linear combination, the linear transformation applied to a linear combination can be replaced with the linear combination of individual applications of my linear transformation T, like so. Here's a step of induction, and that's many more steps of the same induction principle. And that is true, of course, for any set of scalars, lambda 1, lambda 2, lambda n from my field of scalars, and it's true for any set of vectors x1, x2, xn. Well, again, I'll say it for the last time. I'll say it for the last time again. When you build this linear combination here, you use plus and you use scaling from the domain. This linear combination on the right-hand side, it uses plus and scaling from the codomain. The only thing which is shared between domain and the codomain is the field of scalars.